So this is an I2C update. So this is to try and educate and let people know I've changed this routine. So a Great Cow Basic is a compiler. It's a up on SourceForge, and you can go download it. So what have I done? Let me show you an output, okay? Before I do anything, let's just see it running. So this is an output screen that's coming from a series of devices that are attached to the IC2 network. I'm starting with the demonstration to give you an idea that it works, okay? So I'm going to press the reset button on the chip, and what it's just done in this few seconds, it's actually scanned the 256 potential devices that are sitting on the I2C interface, and it's told me I've got 3 devices. There's 3 because they come in pairs of 2s, and I've been successfully picked one up on a 40, A0 and D0. So it's scanned the whole of the space of the I2C. So how does it do that? The code is extremely similar to the existing code. Very, very similar. Essentially what I've got is the same commands to set up I2C. I've got a master, a port, got the ports for the clock and the data exactly the same, and I've got a new command called disable interrupts. You might need that. I need it in some of my programs, so I've included it in the update, and it just turns off the interrupts during I2C interfacing. You can turn it. If you do not put this command in, it will be exactly the same as it was in the previous version. There's a lot of code in here just to set the screen up, which is what we saw before. And essentially, the new command is extremely simple. It uses I2C start exactly the same as before. I2C send, and I'm going to send it a device ID as a piece of information, and then I'm going to stop. Oh, I've got 2 stops, so we'll take that stop out because we're going to recompile this anyway, just to make sure it all works. I'll take that stop out. Before, in the previous version, I wouldn't have taken that out. I've been very, very nervous to take it out. Okay. Essentially, what it then does, because there is a new function rather than a subroutine, it actually returns data back from the I2C send function, and that function returns you the acknowledged signal back from the devices, and you can test that device. If it's acknowledged, you get a particular code. If not, you get another code. So we're just going to recompile it up. So what I've got here is cut the routines, a new IC2C.h low-level file, and a couple of support files. That is just about to, that will just I'll just quickly program that. There we go. We'll quickly write that out. Then we'll have a look inside of here, and we'll see that it's just reprogrammed it. Now you might not believe it's reprogrammed it, because how do I end of device search? I'll put a different version number on it, okay, just to prove it. 0.81. I'll compile it up. I'll pick it up when it's good and ready, and I'll write that out. There we go. So what's it doing? Okay, quite important. Now it's searching 255 addresses, but we know something, that for me to demonstrate this, that it's working correctly, I'm going to actually just change the device IDs so that we have a chance of seeing it. Now we know there is a device sitting at hex 40, which is decimal 64. So I'm going to change this to 65 and 63. And by doing this, right, it's going to compile a piece of code that does 4 I2C data sends, and we can actually see those in a moment. We'll wait for it to compile. Oh, I have to turn this on, really, get it over and done with. There we go. There we go. So he only found the 2 because I've now limited it to hex 3F through to 41. That's correct. But what I've actually got is a camera set up, so you can actually see it. Okay, so I'm just going to clear down my protocol converter. It's small but effective. Okay, so it actually didn't capture all the transactions because it's so fast. Okay, it is happening so fast that my protocol converter isn't even seeing it. Oh, yes it is. Really stupid of me. I'm really stupid. One moment. Never do live demos. So, what we can see here is that it sent out 3 commands, and those 3 commands, I'm just going to recompile again. Those 3 commands, where's the camera gone? Those 3 commands, because the high bit is not set, is a 7-bit number. When you send out 40, it actually comes out on this screen as 20. Okay, so we're just going to run it once more, and then I'll talk you through the logic. Okay, all right, just to show you it working. Reset the chip. So good, there we go. So we it's a 7-bit number that's addressed on the I2C bus. So we see here effectively 3F not been acknowledged. There's an open brace here in my decoder, and that means it has not been acknowledged. 20 is the actual device 4's hex 40 with the 8-bit. I've just added it on, and the right arrow tells me that it's an outgoing request, a write request. 20 with a less than sign means it's a read request on that port, and 21 I've got back a NAC. So I now know, because I can see that this transaction is completely valid, because I can see there's no errors on here. I'm sending out data, and this means that the bits on the channel are very, very stable. Okay, really stable. What I can do is because I now know there's a device on there, I can just send it commands. I could send it I2C send commands, and I'm pretty certain it's going to be robust. So let's look at a bigger program. Okay, all right. This program is the test program I've written. We know that there are a series of devices on this I2C bus. So I've written a library for an MCP device, one for an EEPROM device, and one for a clock. And this code, the same code at the top here on the screen, look. This code essentially sets the clock. It can read the clock. It can do whatever you like. It's going to turn on some pins on the MCP device. I'm actually going to turn some LEDs on that I can see on my right, and then I'm going to read the state of that device. And why I'm doing this is because I want to make sure that the device works correctly. On the previous code, if you did a memory device followed by an MCP, it would not work. So I can sort of put this wherever I like now. This is not important, so I'm going to sort of put that in here. That's fine by me. I haven't done this before, but it should be fine. Then I'm going to do some EEPROM reading and writing. I could do it randomly, but I'm just setting it to 56. I like 55 because 55, hex 55 is 1 bit on, 1 bit off, and I can see that on the device. I write to another memory address, memory address 2. I read it back in, and it's just going to loop around of quite a bit. Now I've got some other code down the bottom here, which is writing out hundreds of thousands of memory addresses just on test. So let's just compile this piece of code up here. We'll just stop that there because I just need to load that in. So what we're going to see now is a slightly different screen. It's going to pop it out. This is what I've just changed to version 3. Those are the bytes it sent out. So now it's showing us an FF, which is the state of the LEDs. I posted a 55. I wrote a 23, read a 23, and then reread the first number I wrote. If I just set this to auto load, I am going to change this because it's always a bit worried when you see an FF, right? Okay, you think, oh well, it's not working. So I'll recompile that, and I'll just set the LED value on that MCP device to 7. And so it's just compiling that up. So currently it's just looping through this code and it's writing to multiple devices. And in a minute we can actually, it's so fast of course. Now we know, we can see that the result 0 is 7, and that 7 equates to the current state of the LEDs, and I look across and they're actually at 7. So what's happening on the port? It's quite a lot going down, but there's no errors, okay? We're going to see one screen. Okay, let me walk you through it. Device 20. Device 20 is the, I should be able to work it out by just looking at it, actual fact. I can't, I'm too tired. Let me have a look in here. These are the pieces of code. Can I open all these up? Oh, good. Let's have a look. All right, 40. 40 is the memory device, okay? Is the MCP device, sorry. So that's a 20 because the top bit's been wiped out. And this says set the ninth bit of this device to the value 7, and it responds out with the plus, which is a write, okay? It's received and acknowledged, there's no error conditions. Device 68 is prime, so we just work that out. Device 68, this is the way I do it, 68 times 2. It's the D0 device, and the D0 device is the DS, it's the clock. So this says 68, write out into memory location 0, 0, 36, so that's 6, 30, and that's the time that we set the clock to. It then returns back to device 20, that's 40, which is the MCP, and sets, does a read on that value, on a value. It says send me the byte value, or the value of NRAM on 9. The 20 then responds with a request, and then it sends back 7, and that minus it says that's an acknowledge back to say it's complete. It then swaps to device 50. Device 50 is then set to 55. That's a write into 55 with an acknowledge. It then writes, as you can see, there's no error conditions now on the whole transmission, and we should see a repeat of some of this code because it's actually just looping around here. And so I'm trying to find where one's similar. And so return of a 7. Oh, I think it repeats there. Look. That's where it repeats there. 20, 9, 7. That's the top of the SOP. 60. 68, 0, 0, 3, 6, 29. So there's no error conditions. On the previous version, this would have been very hard, just impossible. I've written this code in 10 minutes this evening. So how does it work? Let's have a quick look. Okay, so you need to replace your I2C dot file. It needs to be replaced. Okay, it's in the low level folder. It's a bolt-in replacement. I have not deleted the old code. It's still in there. So if you don't like what I'm sending you, you can just copy yours back on top. Okay. A couple of things that you just need to be aware of. Okay. I'll give you these 4 files. Okay, and they are in beta. Okay, so you need the utils one that does some shifting, and the rest of them are device physicals, and we'll write a load more of those to be very specific. Okay. So how do you use it? Very similar to before, but there's just no errors. Okay, it's a function called senderbyte, and this is senderbyte. It's start, send, stop. There's no acknowledge because all the acknowledgements are all held within the new routines. They handle it all in there. Now, what you can do, if the protocol requires it, on a receive, you can send it a NAC. That is in the specification. It's nothing that I it's that you need to do it. You just need to read the specification in the data sheet. It says you need to send a NAC after you've done the receive, and that allows you to do it. And that is how it works. It's almost the same. The difference is, as I said before, is I2C send gives you a result back which you can actually test. You can actually see if you're actually getting a read-write operation, so you can actually handle the error condition if there is an error condition. I have depreciated and removed read reg and write reg. They are very dangerous and not needed. Okay, in my view. All right, it's my view. Okay, they cause all sorts. They were causing all sorts of havoc. Okay, now what else you can do, and you should know, is that I've written these, and these can be adapted, etc., as needed. So, for instance, this 24LCH, this is suitable for high density devices. If somebody wants to write a 24 and for a less than 2K, all you've got to do is just change these codes here, and you'll be well away. You just need to delete this one line here, and it's equivalent to this file, so that works quite well. Device IDs and hardware are all inside of this file, and I've made a choice that says, right, because you may have multiple devices on the bus, okay, you can address a device through EEPROM device _1, MCP device _1, etc., etc., because you may have more than one. DS1307s, not the case. They're pretty hard coded, so you don't get the option there. But you've got to look in here to what the address is, okay? You have to send the address in these new functions. There's no like global thing because these are highly reusable. Okay, so I haven't got a global address or constant. So you have to send it the device, the instruction, and then what you want it to do. They're pretty simple. Okay, I will document them out, but if you want to send out a byte to the MCP device, that's the command. If you want to send something out to an EEPROM, this is the command. You just loop through. If you want to read it back, because it's now a function, I've written functions rather than subroutines. Sometimes I like functions, to be quite honest. I'm a functions guy as well as this in direct writing. Just depends how I feel. But I've done a function for that because you can see the data. You send it 3 parameters and you get the data back. The code itself, let's try and just have a quick look at that. It's a complete rewrite of the master. I haven't touched the slave. Okay, don't need to touch the slave. You may have to change these delays if you want to speed it up, but I've set it up for the 1307 and it should be fine. Okay, for the rest, don't play with the constants. You've got a couple more constants in here, don't go playing with them. This is all based upon the assembler that I got from Microchip earlier in the week. So I took this bit banging code and converted all this bit banging code in C into quick basic and tested it. Okay, so it's basically this code here, and I should be able to make this run on 12 bits as well. It shouldn't be hard to actually port it because it's all the same basis. It should be pretty simple to get this working on say 12-bit devices now. Okay, or PIC 12 devices. I haven't done that at all. It's PIC 16. It's the same rules as before. So what you've got is I2C start the same, I2C stop the same. You don't go playing with these bits out because they're all handled very differently. So these are bits in and bits out that go that handle the clocking, etc. As I said before, I2C send takes in a byte and actually returns back its ACK status. Okay, which is quite useful. It's actually, you need it at some points. There's an I2C receive, which takes a byte, and you can send it this ACK, and ACK is a protocol ACK that you need to send for certain devices that you couldn't do before. Okay. And then there's this thing called ACK poll. Again, you might need that for some devices, and you'll see in the code that the one of these devices, I forget which one it is, I think it's the memory device, it needs to be acknowledged, okay? It has to have a special poll, okay? And I've written that routine, okay? And then underneath that, all the version 1 code is still there. So if I show you this, there is an act poll that's required inside of here, and it's a special poll, it's a special call into this EEPROM. Without that, you're pretty well, it gets pretty well messed up. So what's happening on my little screen here? Oh, still running, no errors. I left it running all last night. It went through a memory device of, here it is, my memory device is a 1 meg memory device, okay? It's a little 1 meg and RAM device. It's extremely fast, no delays required. It's a FM24V10, and no errors at all. Writing bytes in, and I got all the bytes back. Blindingly fast, by the way. There's none of these delays required. Finally, and that's it. So how do you use it? Install the files into your computer. You then need to, if you want to use these, you need to have the util one. Without the util one, it's a utility that does a bit more memory shifting than before. Okay, so bit shifting. You need that. So you don't need that. These 3 are samples. Okay, all right. That's it. I can't show you any more. Okay, I think that's about it. So I'll post all this in a minute. Good luck. I hope this works, because I was so disappointed last week when I spent 3 days trying to figure it out on my decoder, and then I worked out that I might as well give up and start again. Ciao.